Hi, thanks for joining me. Today I'm going to be continuing on with my mini-series on Gaussian Quadrature. Today's video is part 2. I'll leave a link in the description below for part 1. But today I'm going to be talking about the Gram-Schmidt Orthogonalization Process. Now, in part 1, I talked about what we're aiming towards, and I talked about inner product spaces. Today I'm going to be talking about the Gram-Schmidt Orthogonalization Process. So I'll describe it in a sort of general sense, and then I'll sort of move on to how it relates in particular to Gaussian Quadrature. Let's get stuck in. Okay, so firstly, let me define what I mean by orthogonal. Suppose we have a vector space V equipped with the inner product, this guy here. Now, in part 1, I described what the inner product was, so if you've not seen that, go and check that out. Again, a link in the description below for that. We say U and V, where U and V are elements in capital V, are orthogonal if U comma V equals 0. Okay, so this you can perhaps think of an example as the dot product, if you've seen that. So in R cubed, so if our vector space V is R cubed, if V is R cubed, two orthogonal vectors could be 3, 6, 1, say, and then this vector, I'm going to have to think of one on the spot. Let's go minus 1, 2, minus 9. Okay? And the reason for that is when you do the dot product of these two things here, if you've seen the dot product before, so our dot, if our inner product was the dot product, this would be minus 3 plus 2 times 6 minus 9, which is 0. Okay, so these two vectors here would be orthogonal. Okay, now what we're going to do is I'm going to describe the Gram-Schmidt Orthogonalization process, which says we take a basis of the vector space V, provided the vector space V has finite dimension, and we can then construct an orthogonal basis, which means we have a basis, except with the property of this basis is whenever you take two distinct vectors and you put them in this inner product, they're going to be orthogonal, i.e. you put them in this inner product and it vanishes. Okay, so let's move on to that. Okay, so what I'm about to describe is the Gram-Schmidt orthogonalization process. Suppose we have a vector space capital V, and the field that we're on is the reals. Now, in fact, we can choose any field provided the reals are a subset of that field, but just not to overcomplicate things, I'm going to just assume that we're working on the reals, because that's in fact all we need for Gaussian quadrature. Okay, and suppose that we have a basis of this vector space V, which is going to be E1, E2, all the way up to En. Now suppose also V has an inner product, this guy here. Now what we want to do is construct a new basis, so we're going to call this new basis F1, F2, F3, all the way up to Fn. And what we want the property that Fi, Fj equals 0 whenever I doesn't equal j. So in other words, this basis is going to be orthogonal. So we want to be able to construct this. Now how are we going to go about doing this? Well, we're going to start with this basis and use it to construct our new basis. So the first vector, F1, is simply going to be E1. Nice and simple. Now we want to have F2 be so that when we do F2, F1, we're going to get 0. So F2 is going to be E2, then plus some constant times E1. The constant, I'll write it in just a second, it's going to be, it's going to be minus something times E1, and this something here is going to be E2, E1, all over E1, E1. Now, a few things to note. Firstly, is this fraction well defined, i.e. is the denominator ever 0? No, it's not, because E1 is not 0 because it's in a basis, and this thing here is an inner product, so whenever you're not 0 and you're in a product with yourself, you're going to get something strictly greater than 0, so that makes sense. And now also notice that this fraction here is just some number. It's a quotient of two real numbers where the denominator is non-zero, so it's going to be some nice real number. So we've just got F2 is E2 minus some constant times E1. So that's perfectly fine. But remember, we want this property here, but in the case I equals 2 and j equals 1. So let's just check that. F2, F1, or what is that? Let's just plug these two things in here. I'm going to call this constant here C for now. So we get E2 minus C E1, E1. Okay, Now remember, by the linearity property, linearity in the first component, we can write this as E2 E1 minus C times E1 E1. Okay, but remember C is this guy here, this constant, E2 E1 over E1 E1. So when I plug it in here, the E1 E1 here and the E1 E1 here cancels. So I've just got E2 E1 minus E2 E1, which is of course 0. Okay, so F2 and F1 are orthogonal. Great. Now what we're going to do is construct F3. Because I've run out of space, let me wipe this off and then we'll continue. Okay, so we've just derived F1 and F2. Now notice that for F2 here, I've written it slightly differently. I've just swapped the E1s for F1s, but that's perfectly fine because F1 equals E1. And you'll see why I've done that in just a second as I write down what F3 is. So F3 is going to be equal to E3 minus E3 F2 all over F2 F2 times F2 minus E3 times F1 all over F1 F1 times F1. So we've got a lot of similarities in this line to this line. We've got E2 minus some constant times F1 on this line, and this line is E3 minus some constant times F2 minus some constant times F1. And we chose in this case here, we chose the constant appropriately, so that F2 comma F1 was 0, i.e. F2 and F1 were orthogonal. And it's the same thing for this line. We choose these constants here appropriately, so F3 is both orthogonal to F2 and it's orthogonal to F1. Let's quickly check those things here. What's F3 comma F2? Or let's do F3 comma F1 first, in fact. F3 comma F1, let's just write it like so. It's going to be E3 comma F1 by linearity minus this junk term here, this junky constant here, times F2 comma F1 minus this junk constant term here times times F1 comma F1. But let me write that out first. That's E3 comma F1 and then minus this, let me call it C1 term, and then F2 F1. And then this constant here I'll call C1, so that's my C2, sorry. I'll call this constant here C2, this one here C1, so the numbers match up. C1 and then F1, comma F1. Okay, so F3, comma F1 is this thing here, but remember F2 and F1 are orthogonal, so this guy vanishes in the middle. This thing here is just 0. So we got E3, comma F1 minus C1, F1, F1, but C1 is this guy here, so it's E3, F1 over F1, F1. The F1, F1 and the F1, F1 there cancel, so we've just got E3, comma F1 there, and then here E3, comma F1, so they both cancel, and this thing here is 0, so F3 and F1 are orthogonal, and a similar thing tells you that F3 and F2 are also orthogonal. Okay, so this is a vector we can use for F3, and we sort of continue in this manner. We write, in fact, Fj is going to equal Ej minus Ej, comma Fj minus 1 all over Fj minus 1, Fj minus 1, then Fj minus 1, and then minus dot dot dot, and you keep going all the way down to your bottom vector, so it's Ej, comma F1 all over F1, F1, F1. Okay, so you can sort of derive your basis in an inductive manner, and it's not too difficult to check that Fj is orthogonal to Fj minus 1, Fj minus 2, Fj minus 3, all the way down to F1. And then if you continue this to j equals n, you get a basis which is orthogonal. So you'll be able to construct F1, F2, let's call this basis curly F, so F1 all the way up to Fn, which is now a basis for our vector space V, and now it has the property that Fi, Fj equals 0 whenever I does not equal j. And that's exactly what we want from the Gram-Schmidt procedure. Now let me get on to how this relates to Gaussian quadrature. Okay, so now let's get on to how it relates to Gaussian quadrature. We're going to have our vector space V to be the polynomials of degree at most n, and our field F to be the set of real numbers. Now this thing here is a basis for V, so 1, x, x squared, x cubed, all the way up to x to the n. That's a basis for V, because any polynomial can be expressed as a linear combination of elements in this set here. and of course these are also linearly independent. Now, what we want to do is use the Gram-Schmidt Orthogonalization process to construct a new basis, which I'm going to call phi naught, phi 1, all the way up to phi n. These are all polynomials, okay, and we have a few properties which we can derive, or which we can state. Firstly, phi I is a polynomial of degree I. Also, they're orthogonal with respect to, perhaps I should have written this, our inner product is going to be this thing here, fg, sorry my whiteboard is being very shaky today, fg is going to be the integral from a to b of f of g dx. Okay, remember we showed that this was an inner product in the first video. That's the inner product we're going to be using, and we can show, or by deriving, using Gaussian, the Gram-Schmidt orthogonalization process, going from this basis to this basis, we have that the integral from a to b of phi I of x times phi j of x equals 0, or dx, equals 0 whenever I does not equal j. And in fact, we may assume without loss of generality that this integral here in fact equals 1 if I equals j, and that's just by making each of these vectors here orthonormal. So that means that they're still orthogonal, but we're going to divide through by the magnitude. So if these aren't orthonormal already, i.e. have unit length with respect to this inner product, we just look at this basis here, say phi naught tilde, phi 1 tilde, so on, all the way up to phi n tilde, where phi I tilde is defined to be equal to phi I divided by phi I, and the square root of that. Okay, so that's the basis we're going to be using. So it's got the property that each phi I is a polynomial of the degree at most I. It has this sort of orthonormal property here, that the integral from a to b of phi I of x times phi j of x is 0 if I and j are distinct, but 1 if they're the same. Now what we're going to do in the next video is show that each of these phi i's has, so phi I has I roots between a and b, and then we're going to use that to slowly make progress in deriving our Gaussian quadrature. See you then. Have a great day.